Okay, so welcome to this Wednesday sessions. So we just a few words of introduction. So this is already the third day of this workshop. I hope that you enjoy the workshop until now. We will have 5 talks today, and mainly regarding method-based or Monte Carlo samplings and all related to sample average approximation, stochastic programming, and so on. The workshop, basically, each talk lasts 1 hour. So it's approximately 40-45 minutes and followed by questions. We really encourage the discussions, and you can continue the discussions in breakout rooms if you want. Just ask to join some breakout rooms. During the talk, we kindly ask you to close the microphone, except of course for the speaker. You can ask a question after the talk. We prefer to ask everybody to wait until the end of the talk to ask questions. You can raise your hand and ask the question yourself, or you can write your question even during the talk in the chat, and we will read the chat after the talks. And if you have any desire to contact the speakers, don't hesitate to use the chat, and you can also discuss after the speakers, with the speakers of the talks in the breakout rooms. I remind that all the talks are recorded and will be made available for free within a few weeks after the workshop. The links will be sent to you and will be made available to anybody who will want to watch a talk. I hope that you will enjoy the day and the sessions, and that you will learn new things and new ideas, new possibilities of collaborations. Of course, we would have preferred to do the workshop at Montreal, but the circumstances are still there with the pandemic, so we still hope that this workshop will be beneficial for a lot of you. So I will not talk anymore. The schedule is that the talk should start at 9:40. So we will wait until 9:40 for Natasa to present her work. But if she wants to present herself meanwhile, she's welcome.
Well, thank you, Fabian. Thank you for the invitation to this workshop. I'm coming from the University of Novi Sad, that is a city in Serbia. I work in numerical optimization, and today I'm going to present one approach to minimizing finite sums. So, besides working in numerical optimization, I'm also dealing with real-life applications, and I'm deeply involved with the European Consortium for Mathematics in Industry. So the work I'm going to present today is joint work with Stefania Bellavia, Benedetta Morini, and Simone Rebegoldi from the University of Florence in Italy. And we worked on the idea of using an inexact restoration approach to determine a suitable scheduling for finite sum minimizations. So the problem we consider is an unconstrained minimization problem with the objective function that is a sum of some n phi functions. We are assuming that each of these functions is mapping from Rn to R with continuous Lifshitz gradients. And of course, the case we are interested in is the case when n is really large. I guess that you are all familiar that the typical machine learning problems come in this form. So if you have a set of examples, the so-called training set with features and labels, then we have a loss function that is doing, sorry, I thought that the chat is for me. So we have a loss function that is measuring the mistake that we make with our prediction. And of course, our goal is to predict the unseen data accurately. So in that case, Phi is a loss function that corresponds to each observation, and the finite sum minimization actually represents the empirical risk minimization on the training set. The key issue in this story is that n is really large, so computing the objective function and its derivatives is really expensive, and that is not something that we can easily do. So the well-known approach is to work with subsamples. So for some number n, which is a sample size, and which is larger, which is smaller than the number of functions, than the capital N, we randomly select a subset of that cardinality, and then we can approximate the objective function with the subsampled function. We can approximate the gradient of the objective function with the subsampled gradient, and we can do the same thing with the Hessian. Of course, there is no real reason to keep the sample sizes equal for the function, the gradient, and the Hessian. So basically, we can approximate each one with a different sample size. Besides the solving of problem of a very large sum in the objective function, this subsampling actually makes sense for another reason as well, because very often you will have some redundancy in the data. So using all sample data is in fact not necessary. So the main idea is that we try to work with small samples, at least initially when we are still far away from the solution. And that way we hope to save some computational effort. So let me start with a well-known method that I guess everybody knows, that is the stochastic gradient method. That is due to Robbins and Monroe from the 50s last century. So for the sample of dimension S and the positive step size alpha k, we define the new iteration as the previous iteration minus the step size and then the subsampled gradient. Of course, if we take a subsample of the size 1, then we get the basic stochastic gradient method that was actually proposed by Robbins and Monroe. But if we take S slightly larger than 1, then we are dealing with the so-called mini-batch stochastic gradient. It is quite easy to see that it is very cheap to compute a new iteration because you have only a single gradient or a couple of gradients here. So the new iteration is really very cheap. However, to make it work, we need to take diminishing step sizes. That means that the sum of step sizes goes to infinity, but the sum of squares is bounded. You can think of the sequence alpha k equal 1 over k and many modification of that expression. But anyway, it is a diminishing sequence. Of course, since alpha k becomes very small early in that process, then the convergence of the stochastic gradient method and mini-patch stochastic gradient method is very slow. So what can we prove for this type of method? Well, we can prove a convergence in expectations for strongly convex functions, and we can prove also the convergence of the expected gradient for non-convex functions. Diminishing step sizes imply a very slow convergence, but they are actually needed because if we are in each iteration taking only a single gradient or some mini-batch gradient, it is quite clear that we are introducing a lot of variance. So these diminishing step sizes, which are becoming smaller and smaller, have that effect that they are able to deal with the large variance that we are introducing in the process, and they are actually with them we are actually avoiding a large zigzag that would occur if the step sizes were not that small. However, in the last 10 years, we have a number of other ideas how to deal with variance. These are the variance reduction methods. Some of them are listed here, but I have to say that there are many others, and to apologize for all of that I'm not mentioning here. And with these methods, we can take larger step sizes, and we actually get faster convergence because we are dealing with the variance in other way. However, the problem with this approach is that you have to tune the parameters of your methods for each particular problem, so that can be computationally demanding. If we now think for a moment of the deterministic problems, we know that we have two techniques which are very well developed and studied for global convergence of optimization algorithms, that is line search and trust region. So since the stochastic gradient do not rely on any machinery from optimization procedures in the deterministic case, the work that I'm going to present here is actually trying to use some tools that are developed in the trust region methods, and to define sampling that is going to be cheaper than working with the full functions all the time. So what can we do if we try to employ line search or trust region with random models, meaning that we still want to subsample the function, the gradient, or the Hessian if we are working with the second order models? Well, first of all, we have to adjust our criterion for accepting or rejecting the step to the fact that we are dealing with the random models. So we are using stochastic estimates of functions and derivatives. And one possibility is that we actually approximate the objective function and its derivatives with increasing accuracy, but with some prefixed probability. That means that we want to have an estimation Fm of our function Fn. So M is going to be the cardinality of the subsample in such a way that the probability of this error being small enough is always larger than 1 minus Pf. And the same is true for the norm of the subsampled gradient. The key thing here is to notice that these probabilities Pf and Pg are fixed. So we want the fixed probability for our estimations during the whole process, but the accuracy requirements in generally increase through the process. So initially we allow that the approximations are rather loose, so the accuracy is small, but as we approach the solution, we want better and better accuracy. And there is a number of important papers dealing with this approach. So let me concentrate on the trust region methodology that we are going to use here. And I will first try to explain how the trust region machinery works with a random model. So the trust region model in general uses both the function and derivatives, because we are building a model of our function, which can be either linear or quadratic. So the acceptance rule for the step is also dealing both with the function and derivatives. And in our case, these estimates for the function and the derivative are going to be subsampled function and the derivative. And we will employ a technique that is developed for constraint optimization, and that is called Inexact Restoration method. So that is what I'm going to explain in the next slide. So we will require that the probabilistic accuracy that I just showed, so these two estimates, are satisfied only at the end of the optimization process when we use the full function sample size. So the idea is that initially we work with the subsampled function and the subsampled gradient, but gradually we approach the original problem. So if this is our original problem, we will initially try to minimize the subsampled function with the sample as small as we can get good results. And once we achieve the full sample size for the function, then we will require that our derivatives are good estimations with some prefix probabilities. So we will never reach the full derivative, the full sample for the gradient. And in fact, we will show that the sample size needed for the gradient can be reasonably small. So what is the standard trust region iteration? So if we are at the point xk and we have the trust region radius delta k, then we build a model of our objective function, which is in general of this form. So we have the functional value, then the first order term, and possibly the second order term. And we have our trust region, which is defined by the radius delta k. And instead of minimizing the function, we are minimizing this model in each iteration. What are the choices for this quadratic term? Well, one can take either the Hessian or some approximation of the Hessian. So once we solve this model, we have a pk, that is the step, the direction and the step that we are going to move from our point xk. So now we compute if the decrease that we obtained with minimizing the model is good enough. So we compute the reduction that is given by the model. So that is mk of 0 minus mk of pk, and the reduction that we obtain at the new point on the real objective function. So if this is good enough, meaning that the actual reduction is at least a fraction of the reduction given by the model, we say that our step is successful. We define the new iteration, and we take the new trust region radius, which is either the previous one or larger value. On the other hand, if the reduction in the objective function is not good enough, then we declare our step unsuccessful. We think that the step was not good because our model was not good. So we reduce the trust region radius, we build a new model and repeat the whole process. So what happens if we have a subsampled trust region problem, meaning that we don't work with the function fn, but we work with some subsampled function and the gradient. So in each iteration, we choose some sample size, which is smaller than the full sample. We choose randomly the subset of functions that are going to be included in our function estimation, the gradient estimation, and possibly the Hessian estimation. And using this model, which is now a random model of our function, we perform one trust region step exactly the same way as in the classical case. So I'm going to concentrate today on linear models. So we will not use the second order term, and on a ball centered and at xk, and with the radius delta k, we built a linear probabilistic model using a sample size that I denote here with nk. So in the iteration k, we use the sample size nk for the function, and we take some random gradient approximation gk in an arbitrary way, and we build a linear model. So we are going to assume that we have these two estimates, but both estimates are true with the probability Pm, which is fixed. However, we want these estimates to be true only when we are at the full sample. So if nk is smaller than n, we are not imposing these conditions denoted here by 2. Of course, the conditions have to be true on our ball. This idea, the linear probabilistic model in the trust region framework, is not new. It was considered already in a number of the papers. In particular, we rely on the theory developed in the STORM algorithm, published a couple of, 2 or 3 years ago. So the question we try to answer now is how to choose the subsample size nk that will be, that will be used for the approximation of the objective function in such a way that we can work with small samples for the derivatives, work with a small sample for the objective function, at least initially, and still solve the original problem with the full function. To answer that question, we are going to rely on a method that was developed for the constraint optimization, and that we already use in a number of papers that deal with the finite sum minimization. So if we have a general constraint problem, that means that we want to minimize objective function f such that h of x is smaller than or equal than 0. So we have some constraints defined with this h of x. Then we associate with this h of x a capital H of x, which is measuring the infeasibility in some way. So this function is a scalar function, so it gives us a number, because the constraints are generally given as a number of functions, so we cannot express this as a scalar value. And then we define the so-called merit function that depends on x and on the penalty parameter theta in such a way that we multiply the objective function with theta and the infeasibility measure with 1 over theta. So the merit function has both components, the objective function and the violation of constraints. And then the idea is to improve both feasibility and optimality, but in a kind of modular way. So I will try to explain on this picture here. So imagine that these are the level sets of our objective function. We have constraints here, and the minimizer is clearly this red point. And we are at the iteration xk. So what does it mean to have a modular improvement? Well, we introduce an intermediate point, yk, which is such that we look at xk and we try to improve feasibility of xk. So we get a point yk, reducing the violation of constraints. During that process, we allow ourselves to make some small deterioration in optimality. So when we are determining the point yk, we are improving feasibility with respect to xk, and we don't care too much about optimality. Then in the next step, we deal with, optimality. So looking at the point yk, we try to improve optimality of the point, and we get xk, which has a lower value of the objective function with respect to yk. During that process, we allow that there is a small deterioration of feasibility with respect to yk. But since the modular improvement of feasibility and optimality is designed in such a way that we ask for relatively large improvement and allow small deterioration of the component that we are not looking at, altogether we get a point xk plus 1, which is better than xk. And the merit function is actually taking care of both things. So we adjust the value of the penalty parameter depending on what kind of increase we get in each iteration. So if we have a better increase in optimality, we pay more attention to feasibility in the next iteration, and the other way around. Why we decided to use this approach here? Well, because of this modular improvement. In other words, this method is very good if you have objective function and constraints that are very different in terms of computational costs. So if one of them is costly, another one is cheap, then this combination of modular improvement of feasibility and optimality is giving very good results. So to do that, first we need to reformulate our problem into the constraint form. So instead of minimizing the unconstrained function, we are minimizing a subsampled function with the condition that the sample is full. And then we apply modular improvement of feasibility and optimality. Of course, the feasibility is very cheap because this does not depend on X. So we defined feasibility measure as the difference, relative difference in the sample size. So it is n minus m over n. There are some other possibilities, but this one we can think of this one to make it simple. And then the merit function is subsampled objective function plus infeasibility measure with penalty parameter that is between 0 and 1. Clearly, we need penalty parameter that is bounded from 0 and bounded from 1 because we want to take care of both things, both the optimality and feasibility. So how does it work for this particular problem? Well, in the restoration phase, we have to improve feasibility. So we take nk plus 1 tilde, which is the larger sample size, so it improves feasibility. And then we go to the optimality phase. In the optimality phase, we built a model. Since our model is linear, then the solution of the trust region is obvious, so we don't actually need to solve anything. Our model is with a random direction GK, which is approximating the gradient in some way. And since in the optimality phase, we can allow ourselves a little deterioration of feasibility, we built that probabilistic model with some nk plus 1 t, which can be smaller than the sample size that was used to improve feasibility. So here we have some possibility of decreasing the sample size. Then, depending on the quality of this direction that we got from the trust region, we update the penalty parameter, and then we compute the predicted and actual reduction. We decide if our iteration is successful or unsuccessful, and we update the trust region size for the next iteration. Of course, this update again depends on the success or unsuccess of the iteration that we just performed. Okay, so let us consider our problem with constraint. We have a merit function defined in this way. And basically, we choose a function that is measuring infeasibility as a monotonically decreasing function such that it has a positive value for 1 and the value of the function if we have a full sample is equal to 0. So when we reach the full sample, we are fully feasible. As I said, we can think of this function to make it more simple. And then we need to decide what is our predicted reduction and actual reduction for this merit function that we have, given that we are approximating the objective function with a subsampled function. So we define the predicted reduction, the reduction that is going to be given by the model, as the difference between the function and the model, but we have one additional term, which is measuring how feasible we are in that iteration. And then we compute the actual reduction. The actual reduction is, in fact, the difference between the value of the merit function at the old point and at the new point. And then the rule is just the same as usually in the trust region. So if the actual reduction is at least 1 fraction of the reduction obtained by the model, then the iteration is successful. Otherwise, it is unsuccessful. And we go to the update of the trust region size. So the update of the trust region size is going to depend on this value here. So it's going to depend on how good is our model solution pk. But the big difference with respect to the deterministic case is that here we will have that the trust region size actually goes to 0, which is not the case in the deterministic optimization. So in more details, the algorithm looks like this. So we have an indicator if the iteration is successful or unsuccessful. And we have another indicator if we are at the full sample or not. This is important because remember that I told you that we are going to ask that our model for the gradient is good in the probabilistic sense only if we are at the full sample. So this indicator is actually telling us when we need a good model for the gradient. So initially we do the restoration, so we try to improve feasibility. If we are not at the full sample, then this indicator is 0. We look for new sample size, which is larger than the previous one, in such a way that the infeasibility measure is decreased with some parameter r, which is between 0 and 1. So I want a linear decrease in infeasibility. Otherwise, if I am already at the full sample, then if my iteration was not successful, then I don't change anything. I don't change the sample size because I have the problem in the optimality part of the algorithm. Then for the optimality phase, I look for a new sample size that can be lower than the sample that improved feasibility. So I allow myself to be a bit loose here. But that new sample size is actually connected with the trust region size. So as we are going to show that the trust region size goes to 0, we see that we can profit from decrease in feasibility only at the initial phases of the algorithm, which was the main idea. Then we look for the gradient approximation, GK. We built a linear model and we actually have the direction PK. And again, if we are at the full sample size, we need to check if the model is good. If the model is not good, then we reduce the sample size and we repeat the optimality phase. But we are doing that only when we are already at the full sample size. Then we update the penalty parameter. We compute a new value of the penalty parameter in such a way that the model reduction is at least a fraction of feasibility improvement. And then we decide if we are going to accept or reject the step. So if actual reduction is good enough with respect to the model reduction, we have a successful iteration. However, here we have the additional check. So if this fk is equal to 1, that means that we are already at the full sample. Then we want our gradient to be at least a constant multiplied by the trust region size. Remember that we will show that the trust region size is going to 0. So this actually does not prevent gradient from going to 0, but it is important condition when we are at the full sample size. So we defined a new iteration. We changed the trust region size in such a way that we allow increase if the trust region is large enough. So we are still not at the final stage of the process, and otherwise we keep it the same. we put the flag at the successful iteration and we repeat everything. If the iteration is not successful, then we don't change the sample size. We decrease the gradient the trust region radius, and we go back at the step 1. So what can we prove for this kind of algorithm? If you look once again at these rules that govern the sample size, the sample size can be increased and decreased in each iteration. So it is not obvious that we will reach the full sample size. However, perhaps even more important question is what is happening with the sequence of penalty parameters, because looking at this expression, you cannot say what is going on with the sequence of penalty parameters. And if the penalty parameter would go to 0 or to 1, then the merit function would not represent both the optimality and the feasibility of the problem which we want. So, assuming that all our subsampled functions are bounded on a closed and compact subset omega, we can prove that the sequence of penalty parameter is positive, non-increasing, and bounded from below, meaning that the value of the penalty parameter never goes below some theta bar, and therefore the merit function is well defined. Then, since we are considering the problem of minimization, it is natural to assume that our functions are bounded from below. The infeasibility measure is a bounded function which is decreasing. So we can always find a constant sigma in such a way that this term is always non-negative for all sizes of samples nk. And this fact allow us to define a Lyapunov function of this type. So we have the merit function that depends on the iteration, sample size, and penalty parameter, plus this constant, which always exists. And then we have the trust region radius squared. So if we have both of these assumptions satisfied, meaning the assumption on the functions and the assumption on the feasibility measure, then we can prove that Lyapunov function satisfies this kind of relation for all iterations. Assuming a bit more that the functions are continuous with Lipschitz continuous gradients, and that our gradient approximations are just bounded from some subsampled approximation of the gradient, which is really not a problem, because this is an arbitrary constant. So basically we are saying that all random gradients are bounded. Then we can prove that the trust region radius goes to 0, and that actually means that for a k sufficiently large, we are at the full sample. Now, another thing that we can prove is actually the following. So if we have all our assumptions satisfied, and if L is an iteration where we reach the full sample, so from that point on, we are using the full sample. And then if our model of the objective function is good enough, with good enough meaning that it depends on the quadratic of the trust region diameter, and random gradient is good enough estimation of the full gradient, with good enough here, meaning that it depends on the trust region radius. And if these two estimates hold with a probability which is larger than 1/2, then almost surely we have that the sequence of gradients converges to zero. So we have a limit subsequence which is converging. So the important point in this statement is the fact that we are asking for increasing accuracy with fixed probability, but only when we are at the full sample. So before reaching full sample, we can use relatively loose approximations. So let me show you what we can get with this kind of approach. So we consider the classical problem in machine learning. We introduce the stopping criteria that we stop if the gradient estimation is small enough, or if the difference between two consecutive values of the objective function is small enough. We define the classification error, and we run 50 independence runs for each of the test problems that I'm going to show you. So first of all, we are interested in the behavior of the sample size. So for subsampling the gradient that we are going to use as the search direction in our linear model, we tested two possibilities. So, three possibilities. One is 10% of the functional sample size, then 20% of the sample size of the function, and the same sample size as used for the objective function. So these are the test cases that we considered, and we measured the cost in terms of full evaluation of the function and the gradient. We measured the testing error, and this last column in all three cases is perhaps the most interesting one, because it is telling us in how many of these 50 runs we stopped before reaching the full sample size. In other words, we get a satisfactory result without using the full objective function. As you can see, these numbers are pretty large, relatively close to 50, which was the number of runs. And of course, we see that the method is actually performing the best when we use 10% of the functional sample size to subsample the gradient. So the demand on the gradient subsampling is really not large. Then in the improving feasibility in the restoration phase, we could increase the sample size in different manners, depending on what kind of decrease in feasibility we want. So again, we tested three cases, increasing for 5%, 10%, and 20%. We report the same kind of results. So the cost, the error, and the number of runs where we terminated before the full sample size. Again, slow increase in feasibility is preferable with respect to the cost, but also with respect to the early stop, to the stop without reaching the full sample size. And finally, here are the results with respect to the initial sample size that we are going to start with. And again, we see that 0.1% of the full sample was the best possibility to start the algorithm. So here I show what is actually going on with the sample size between feasibility and optimality phase. So this dash is a sample size that we take in the feasibility phase. So that is always increasing. And nk plus 1 is the sample size that we use in the optimality phase. And you can see that it can be really smaller than the sample size used in the feasibility phase. Furthermore, in this case, we have a really huge decrease of the sample size at iteration number 5. So we are really working with small samples for a large number of iterations, and therefore we are saving a lot of computational work. Well, this is the same thing. And I will end this talk with comparison with the trust region method proposed in this paper, which is a kind of normalized trust region. So depending on the size of the gradient, you take a different step size to get the new iteration. So here is the graph, which is showing the classification error on the testing case and on the training set. So this is the training set, and this is the testing case, the testing set. For different values of this parameter that is here appearing here in the trust region method by Curtis, Scheinberg, and Shi. And the red line is the method that I just presented. Sorry, red but dashed. So what is the key point of these graphs? You can see that for two different data sets, A9A and this one here, we get actually different pictures. So the Trish method depends largely on the value of the parameter alpha, and the behavior is really different in two data sets. While the approach that we presented is adaptive and therefore has more or less a constant behavior on both problems. Of course, this is true for all data sets that we tested, so I'm just showing two of them here. And that is actually our main message, that using the adaptive parameters that are somehow natural, that are generated from the method itself, is robust and at the same time comparable with other methods of the similar kind that depend on many parameters, and tuning the parameters is a cumbersome work. So if you let me to conclude, I try to present an adaptive stochastic first order trust region method that is based on the subsampling that is coming from technique developed for constraint optimization problems that is called Inexact Restoration methodology. And the main advantage is that there is no need for parameter tuning that depend on a particular problem that we are solving. So our model was a probabilistic linear model. We reached the full precision in the objective function after a finite number of iterations. So we are actually solving the original problem, but we managed to work with smaller samples for a long time. Therefore, we gain in computational efficiency. We have convergence results which are in line with other methods of that kind, and reasonably good numerical experiments. Hope I didn't extend my time, but thank you for your attention.
Thank you very much, Natasha. Well, we still
Was I too long?
No, it's okay. It's a bit longer than what we expected, but it's okay. We still have time for questions. And by the way, there are some questions in the chat, mainly from Sven Leifer. So, Sven, if you want, you can read your questions.
Okay, I was going to summarize them a little bit. So the trust region methods, the convergence for unconstrained optimization, that's well established. And so the trick then is to understand how the subsampling affects the convergence, or whether you can still prove convergence for trust region methods. Yes. And the main question I have really is, is there a constructive way of detecting how to choose the parameters? So you in your theorem, for example, you make the assumption that with probability 1/2, you satisfy these two conditions that ensure convergence of trust region methods. But how do you ensure that assumption? And related to that maybe is the question, you form this, you phrase the whole problem as a constraint optimization problem, but a constraint is not really on an optimization variable. It's on a categorical decision, on a decision, how big is my sample set? And that's not something you can relax. So trust region theory doesn't apply in that case.
Yes.
So my question is, how do I ensure that I get this probability 1/2?
Well, I don't have a good answer to that, because if we try to use any kind of estimations that are available, we end up with something that is very pessimistic. So I don't have a really good answer theoretically to that. I can only say that our tests were really reasonable, in a sense that 10% of functional sample works for the gradient very well, and things like that. But theoretically, if you try to put any available estimation, it is going to be a large number. And regarding the constraints, that is categorical. In fact, that was the main reason that inexact restoration approach gave good results here, because that approach is working well if you have a very different objective function and the constraints in the term of computational cost.
Okay. Thanks.
Welcome.
Thank you, Sven. Thank you, Natasha. Tito même de Melo that have resistance, so I will propose that Tito unmute himself so he can ask the questions.
Okay, thank you, Fabian. Thank you, Natasha, for the presentation. I was wondering what is the role of the variance of the estimators in the algorithm, right? Because suppose your phi i's are very different from each other.
Mm-hmm.
Right? So for different i's, I mean, so when you take this subsample, I mean, potentially the estimator will have a lot of noise comparing to what you get with the full sample. But I didn't see that playing a role in the algorithm. So how do you do that?
Well, actually, we are not measuring the quality of the approximation. We are rather playing with the sample size, and if the approximation is not good, if there is a lot of noise, a lot of variance, then it is likely that the trust region step will be simply rejected. And so you will that is the way that you will recognize that your model is not good.
I'm not sure, right, if the trust region be large, because the estimators being noisy, anything could happen, right? With the ratio, when you do the ratio comparison, anything could happen, right? If
yes.
You could end up with a small value or large value. So I wonder if, in practical terms, if you observe that, for example, in the experiments.
Well, not really, not really. I mean, we didn't even report the variance of the results in our tables, because we really didn't observe a large variance in the errors, for example, in these 50 independent runs that we did. It probably has to do with the fact that we tested a function that is coming from, well, this is the problem that we tested. And the data sets are more or less reasonable. So my guess is that we didn't, that the results might be a bit different if, for example, we took a different kind of problem.
Mm-hmm. I see. Yeah, because in that case, the choice of the sample size could be affected by the
yes.
problems.
Yes.
I see. Okay, thank you, Natasa.
Welcome.
Thank you, Tito. Thank you, Natasha. Just before I check, is there any other question in the audience? I don't see any entities raised. Only see comments saying that you you share a lot of knowledge in your talk.
Thank you.